Welcome, everyone. Now, be honest with me for a second. Have you ever been sitting there staring at a massive algebra equation in your Cambridge IGCSE Mathematics past paper, maybe syllabus 0580 or 0606, and just wondered who actually came up with all these strict, unforgiving rules? It's so easy to think of mathematical functions as just, well, another tedious topic you have to memorize to get your target grade, right? But what if I told you that modern mathematical concepts, especially the function, actually stem from an ancient, deeply human desire for order, fairness, and reliability? Today, in this explainer, we are going completely back to basics. We're going to break down the true concept of mathematical functions, tracing their roots from ancient philosophy straight through to the absolute core of your modern algebra syllabus. By the end of this, you won't just know how to solve a function, you'll understand exactly why it works. Okay, let's dive right into this. So here is the roadmap for our journey today. We're going to start with the ancient quest for order, then move into defining the function properly. After that, we'll tackle domains and ranges explained, which is a huge point where students drop marks, followed by the rules of mapping, when mappings fail, and finally, we'll wrap up with the shape of functions. Let's get moving.
Section 1. The Ancient Quest for Order. We're heading back to mathematics in 1605 BC.
To really understand why mathematics is so heavily structured and strictly graded today, we have to travel way back. I'm talking early Han Dynasty around 165 BC. We need to meet a brilliant guy named Cheng Chung. What you're seeing here is a page from his truly groundbreaking textbook, The 9 Chapters on the Mathematical Art. Now, this wasn't just some local pamphlet that a few people read. It was the definitive Chinese mathematical text for literally centuries. Its teachings spread like wildfire, heavily influencing the Far East, making its way to India, the Islamic world, and eventually right into Europe. The very foundation of the math you are doing today, the stuff you are getting tested on, has its roots in this exact historical document. You see, Cheng Shang had a really powerful philosophy. He wrote, "For a civilization to endure and prosper, it must give its citizens order and fairness." He wasn't just sitting in a room theorizing in a vacuum. He was deeply, fundamentally concerned with the ordinary lives of everyday people. He used mathematical ratios and strict proportions to establish practical, real-world fairness. We're talking about calculating exactly how rice and other cereals should be planted in proportion to society's needs, and making absolutely sure that taxes were calculated and paid fairly. To him, mathematical order meant societal order. If the math was predictable, society was stable. And this brilliantly illustrates just how incredibly advanced this book was for its time. Just look at these achievements. The 9 chapters utilized the full decimal system, completely integrated with zero and negative numbers, which was revolutionary. It proved Pythagoras' theorem, included step-by-step solutions for algebraic simultaneous equations, and outlined incredibly complex geometric proofs. This ancient text set the stage for the strict, predictable rules we completely rely on in algebra today. It established the fact that mathematics is a system of absolute, reliable truths. Before we continue on to how this creates the functions you'll see in your exams, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. All right, let's move into Section 2, defining the function. This is where we talk about mathematical order. So we are going to connect Cheng Chang's philosophical quest for reliability directly to the modern concept of a function. In algebra, a function is the ultimate expression of that ancient desire for predictability. So let's establish exactly what a function is, because examiners love testing your understanding of this. By definition, a function is a particular type of relationship between two variables. But the absolutely crucial part is this. Each value in set B, which we call the range, is produced from exactly one value in set A, which we call the domain. Think back to Cheng Chang's fair tax system for a second. For a tax system to be fair, it has to have a strict, highly predictable rule, right? If you make X amount of money, you pay Y amount of taxes. There shouldn't be 2 completely different tax bills sent to you for the exact same income. That would be chaos. That predictability, that ironclad rule of one input gives one specific output, is the very essence of a mathematical function. Just to make sure we are crystal clear on the terminology before we move on, because you'll see these words all the time. Set A is your domain. I really want you to think of the domain simply as your inputs, the starting values you are actively feeding into your equation. Set B is your range. Think of the range as your outputs, the resulting answers you get after the mathematical rule has its job. Domain is what goes in, range is what comes out. Simple as that.
Moving on to Section 3, Domains and Ranges Explained. Let's look at the actual transformation.
Let's actually see these terms in action with a practical example you might pull straight out of an IGCSE 0580 syllabus. Here we have a very standard familiar linear equation. F of x equals 2x plus 3. The rule here is incredibly simple, but perfectly rigorously strict. Whatever our input value is, our x, we multiply it by 2 and then we add 3. That is the reliable, unchanging order of this specific function. No surprises, no tricks.
Now, let's actually map it out so you can visualize the transformation. I'll guide you through this. On the left side, we have our domain, our x values, ranging from -1 to +3. Let's apply our rule. If we input -1, we multiply by 2 to get -2, add 3, and boom, we get a range output of +1. Input 0, the output is 3. Input 1, the output is 5, and so on. Notice how perfectly orderly this is? This specific constrained domain maps out to a highly predictable range of outputs. There is zero ambiguity here. Now, before we look at different types of mappings, I want to drop a huge tip directly from the source material that will save you marks. It's an important convention to remember. If a mathematical problem gives you a function but does not specify a restricted domain, you have to assume it is for all possible real values. And remember, changing the domain will always produce a different range. Your outputs are entirely dependent on what you are allowed to input. Quick pause right here. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to at acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions.
Okay, let's get back to it. Section 4, the rules of mapping. We're going to compare one-to-one versus many-to-one functions. Here we can clearly contrast these two entirely valid types of mathematical mappings. On side A, we have the one-to-one mapping. This is what we just looked at with f of x equals 2x plus 3. Every single input has its very own unique output. It's a straight line of predictability. Nobody shares an answer. But take a look at side B, the many-to-one mapping. We're using the quadratic example f of x equals x squared. Here, multiple different domain values can actually generate the exact same range value. Now, you might be scratching your head asking, wait a minute, doesn't that break the rule of predictability we just talked about?
Well, let's walk through the math to see exactly why it does not break the rules. If we consider a domain from -3 to +3 for our function f of x equals x squared, let's look at the extremes. Inputting -3 results in +9, because a negative times a negative is a positive, right? But inputting +3 also results in +9. Two completely different inputs led to the exact same output. But, and this is the absolute crucial point you need to understand, it is still a perfectly valid function. Why? Because when you input -3, it only ever gives you 9. It never gives you 9 on a Tuesday and 12 on a Thursday. Each individual domain value still points to a single, highly specific destination. It's totally fine if two different starting points lead to the same house, as long as each starting point only has one road leading out of it.
Which brings us to Section 5, when mappings fail. Let's look at breaking the rules. Now that we deeply understand what a function is and how it rigorously maintains order, what happens when mathematical chaos enters the picture and actively breaks the rules? I want to pose this question directly to you based on everything we've covered so far. Does every mathematical relationship equal a function? If I just quickly scribble an equation on a whiteboard linking x and y, is it automatically a function? The answer is a hard no. Take a look at this relationship right here. Y equals plus or minus the square root of x. This is absolutely not a function. Let's test it. Let's say our input, our x, is 9. The square root of 9 is 3. But because of the plus or minus sign built into the equation, our y could be +3 or it could be -3. This totally fails the ultimate test. A single input in the domain, just the number 9, has suddenly created two completely different, wildly unpredictable values in the range. It lacks the basic order and fairness that Chang wrote about centuries ago. It is a relationship, sure, but it is not a mathematical function. To make this super easy for you, especially under exam conditions, here is a simple two-step visualization to mentally test literally any equation you encounter in your studies to see if it is a true function. Step 1, input a single value from your domain into the equation. Step 2, check if it produces only one value in your range. If your one input gives you multiple outputs, it fails immediately. It's really that simple. One input must yield one definite output. Section 6, the shape of functions. Let's tie this directly into the Cambridge IGCSE curriculum. Let's bring this all together by linking these foundational rules directly to the actual shapes and graphs you are going to need to recognize, manipulate, and draw in your studies. Here's the core list of function types you are expected to master. We have linear graphs, which make perfectly straight lines, quadratics, which give us those smooth U-shaped parabolas. We have cubics, reciprocals, exponentials showing rapid growth or decay, and trigonometric functions like sine, cosine, and tangent that create beautiful repeating waves. Now, I know looking at a list like this all at once might feel a bit overwhelming, but I really want you to remember the fundamental thread we've been following today. No matter how incredibly complex the graph looks, whether it's a simple linear line or a wildly curving trigonometric wave, every single one of these equations obeys the exact same fundamental law of order: one input, one output. They are all at their core mathematically reliable. And this beautifully illustrates exactly why all of this matters outside of the classroom. Just look at the complexity of a fractal image. The strict, orderly mapping of functions isn't just an arbitrary topic designed to frustrate you on a Tuesday morning exam. It is quite literally the hidden architecture of the universe itself. From the perfect spirals of a pine cone to the massive orbits of planets, the natural world relies completely on the predictable, ordered inputs and outputs of natural laws that we simply describe using mathematical functions. Listen, students who truly understand and implement these mathematical strategies see an average improvement of 2 entire grade boundaries. But that only happened if they practice consistently. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to at acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for mathematics and the biggest challenge you're facing right now. Our team responds to every single comment. Which leaves us with one final, very important thought. The rigid rules of algebra you are studying today are part of a massive, unbroken chain of human knowledge stretching back thousands of years to brilliant minds like Chang Sheng, who literally used math to build entire civilizations. You now hold the very same tools of logic, fairness, and predictability in your hands. So, if ancient civilizations built their very survival on the strict order of mathematics, how will you use these functions to logically map out your own future? Think about that as you tackle your next past paper. Thanks for joining me on this explainer today. Keep practicing and always keep looking for the order hidden in the chaos.